All right, this is chapter 9, which is stereochemistry, and it talks about the three-dimensional shapes of the molecules. Now, why are we interested? Shapes impact biological activity, for example. Proteins, enzymes, why something tastes a certain way, smells a certain way. So what we're going to do is work through is how we determine those shapes and can we predict those from the Lewis structure. There are two ways of looking at that. One of those is easier than the other. Valence shell electron repulsion theory, which is commonly designated VSEPR, and that was derived by R.J. Gillespie in the 1950s. We'll focus mostly on that one, but we'll talk somewhat about valence bond theory, which was derived by Linus Pauling in the 30s and 40s and involves hybrid atomic orbitals. So what are our steps? We're going to draw the correct Lewis structure. We're going to identify that central atom and how many bonds and non-bonding pairs are on that central atom. Count up the regions of high electron density. That's going to be your overall molecular geometry. And then we're going to determine the electronic, and then we'll determine the molecular. The molecular is the shape of the molecule if you ignore the lone pairs. Now, the lone pairs do impact the shape just a little bit, so we'll talk about that. And then we'll determine the hybrid orbitals according to valence bond theory. And we'll repeat that procedure if there's more than one central atom. So VSEPR theory, you're focused on regions of high electron density. Electrons are negative, they tend to repel one another, so you're going to have the geometry that is going to minimize that repulsion. There are 5 basic shapes. We're going to look at electronic geometry. That's all the regions of high electron density around the atom. The molecular geometry is just the shapes of the atoms themselves around the central atom. There are 5 basic geometries, as we mentioned: linear, trigonoplanar, tetrahedral, trigonobipyramidal, octahedral, and they all have differing bond angles. We'll talk about the shapes here in a second. But linear is 180, trigonoplanar 120, tetrahedral 109.5, trigonobipyramidal 90, 20, and 180. And then octahedral 90 and 180. And we'll talk about how each of those angles play into the shapes. Okay, these are the geometries and some subcategories of each geometry. So you can see the electronic geometry and the molecular geometry. So they're based on the original amount of domains. So if you only got 2 domains, then it's going to be a linear, and it's going to be an sp hybrid under valence bond theory. So you got 2 bonds, 0 non-bonding pairs, and in the time where you got 0 non-bonding pairs, the electronic geometry and the molecular geometry have the same name. And that goes for all the geometries. You get 180-degree bond angles, and carbon dioxide, like we drew before, is a good example of that. If we move on to trigonoplanar, you got 3 total groups, and we call it trigonoplanar, and they're all sp2 hybrids. So if you got 3 and 0, it is trigonoplanar, and it's got 120-degree bond angles. Something like our boron trifluoride would be a good example of that. Now, these hybrid orbitals are s and p orbitals, and they overlap to form a hybrid orbital. We'll talk a little bit about that in a few minutes. So you got 2 and 1. Now, if you got 2 bonds, 1 non-bonding pair, it still adds up to be 3, but it's bent. Now, the bond angle, because the non-bonding pair will squish in just a little bit, and it'll be a little less than 120 degrees. The nitrite ion is a good example. Now, if we look at tetrahedral, we got 4 total groups, being tetrahedral, sp3 hybrid, so 1s and 3 different p orbitals. 4 and 0 is just plain old tetrahedral, 109.5-degree bond angles. Now notice that molecule can't be flat anymore. The wedged line indicates that atom is coming out towards you. The dashed line indicates it's going away. These 2 solid lines indicate the plane of the screen. And you can see that it represents a molecule that's not flat for the first time. And then if you got 3 and 1, that's trigonal pyramidal. The bond angles are a little less than 109.5 because the non-bonding electrons tend to squish those bond angles just a little bit. Ammonia would be a good example. And again, you see the wedged and the dashed lines. If it's 2 and 2, then it is bent. But it's a different bond angle than the linear molecule, and it's a different bond angle than this trigonal planar bent. And so the angle is different, even though they call them both bent. And so you need to make sure when you write down your answers, make sure you indicate which one it is you're talking about. Water would be a good example of tetrahedral and bent. So all those obey the octet rule. What about ones that disobey the octet rule? You got 5 total groups. Then we're talking about trigonal bipyramidal. And so you've got one group that is above and below, and then you got a triangle plane in the middle. 5 and 0 is just plain old trigonal bipyramidal, and you got 90 and 120. You got 120s around the center triangle, and then 90 from top to the middle. 4 and 1 is the seesaw. If you rotated that a little bit where these two formed the wedge on the seesaw and these were the planks that you sat on, it would kind of look like a seesaw. You got 90 still right here and here, but then, and then 120 here, but then it's a 180 from top to bottom. T-shaped has 2 non-bonding pairs, 90 and 180. I don't have the triangle plane in the middle anymore. So it's T-shaped. These are 90, and then all the way here is 180. Then if I have 3 non-bonding pairs, all those spaces in the middle are occupied and only have the top and the bottom, so it becomes linear with 180-degree bond angles. Xenon difluoride would be a good example of that. Now if we look at octahedral, 6 and 0 is octahedral sp3d2 hybrid. But it kind of almost looks like a jack, like you would play outside and bounce the ball and grab the jacks. You've got a square plane in the middle and then one atom up, one atom down. And you would indicate that as wedge lines coming out towards you and away in the middle, and then just a flat line up and down. All those bond angles are 90 degrees. 5 and 1 becomes square pyramidal. That is, I lose one off the bottom, and I've still got a square pyramid on the top, 90 and 180. So here to here is 180. The rest of the angles are 90 across within the top. Just along the bottom, you have some 180s. Then if you have 2 non-bonding pairs, then you lose the top and the bottom of non-bonding pairs. You still have the square plane in the middle, and then all the angles are 90 within the plane, and then from one side to the other is 180. Now, as we've been talking about a little bit, the lone pairs or non-bonding pairs or unshared pairs require more volume than the shared pairs. That is, they generate a little bit more repulsion, so it tends to squeeze those bond angles a little bit. Lone pair to lone pair repulsion is, of course, the strongest because lone pairs have more repulsion. Lone pair to bonding pair is in the middle. Bonding pair to bonding pair is the weakest. So the more lone pairs you get, as long as they're not symmetrically arranged around the central atom, you're going to get some squeezing of the bond angles a little bit. For example, in water, the bond angle is more like 104.5 instead of 109.5.